Radian measure. What is a radian? An angle with its vertex at the center of a circle with radius r that intercepts an arc on the circle with length r has a measure of 1 radians, sometimes written as 1 rad. So we're looking for another way to measure angles. So let's say I have this angle right here. I'm going to go ahead and call it theta. I'm going to say that theta measures 1 radian if the radius, so here I'm going to call the radius r, if the radius is exactly the same as this arc length that the angle intercepts. So this length here is also r. If that's true, if the radius is exactly equal to the arc length, then we say that theta equals 1 radian. Theta is equal to 1 radian. So you can see that word radius involved in radian because we're saying that we have 1 copy of the radius here along the arc of the circle. So now let's go ahead and take a look over here. Let's say I want to find an angle of measure 2 radians. So what that means is that my angle has to intercept an arc length that measures 2 copies of the radius. So here's my radius here, and so this is 1 copy of r, and then this is a second copy of r. So I can see 1 copy of r, and then a second copy of r is occurring. So that means that the angle that we're talking about here is this angle theta. So theta would be equal to 2 radians. Theta would be equal to 2 radians. So we can see if I go all the way around a circle, so here we've already had 2 copies of the radius, this would be a 3rd copy, doesn't quite make it halfway. Then we have a 4th copy of a radius, the 5th copy, a 6th copy of the radius, and I have a little bit extra, So I would make it around a full circle 6 times with the length of the radius, but then have a little bit extra to spare. Radian measure. An angle in radians is measured as the ratio of 2 lengths, the arc length over the radius. So if I want the measure of an angle in radians, I would simply take the arc length divided by the radius. So for this example, they're the same. The arc length is r, the radius is r, so that's 1 radian. In this example, I have the arc length is 2r, and the radius is r, so the measure of this angle here, we would call it theta, is 2r over r. The r's cancel, we end up with 2 radians. In this example, we're looking for the measure of this angle here, call it theta. So the arc length is only half an r, and the radius is r, so that ratio, 1/2 r to r, the r's cancel, we end up with half a radian. For this last one, we're looking for the measure of an angle theta that makes 1 complete revolution, goes all the way around. So we're going to call that angle theta. So we need the arc length. Well, the arc length is just the circumference of the circle. So the circumference is 2 pi r, and then we would take the circumference over the radius. So 2 pi r over r, the r's would cancel, and we get exactly 2 pi radians as the measure of the angle in radians that makes 1 complete revolution. But why do we use radians? As the ratio of 2 lengths, the radian is a pure number that needs no unit symbol, so we consider it unitless. The symbol rad is usually omitted. So unless the degree symbol is used for an angle, it is implied that the angle is in radians. So it's usually at this point where I get asked by students, can I just convert everything to degrees? I prefer degrees. Please don't do this. Since radians are real numbers, remember it's a ratio of the arc length to the radius, so it's unitless, radians have a wider applicable use in engineering and science, so it is important to have a working understanding of them. Understanding how to find angles in radians. Sometimes students struggle with radians because of the fractions involved, so let's do a little bit of review. Let's say we wanted to understand the notion of 1/4. So what we would do is consider a whole split into 4 equal parts. So here I have one square split into 4 equal parts. So if I wanted 1/4 of the square, I would shade one of those 4 equal parts. So now I have the concept of 1/4. Let's apply it to a different shape. So here I have one circle, or almost circle, divided into 4 equal parts. So if I go ahead and shade one of those 4 equal parts, then again I have the concept of 1/4. But instead of a square or a circle, we're going to do a non-traditional shape as the whole. Let's say I consider one semicircle as the whole, and I want to split this into 4 equal parts. So I can think about it as a pizza. So I would go ahead and cut it in half, and then cut each of those halves in half again. So let's say this was a whole pizza that was delivered, and I want to split it into 4 equal parts, so these are my 4 equal parts, so 1/4 would be one of these 4 slices of pizza. So I have 1/4 of the pizza, and then this would be 2/4 of the pizza, and then 3/4 of the pizza, and then 4/4 of the pizza, which simplifies to just 1, and the 2/4 of course simplified to a half. So I just want you to go ahead and keep that in mind as we go ahead and take a look at our radians. So here on our circle we can see that our angle measures in degrees go up by 45 every time, and students tend to be comfortable with degrees, but we want to be just as comfortable with radians. So the key is to remember that one complete revolution is 2 pi radians. One complete revolution going all the way around is 2 pi radians. So that means going halfway around must be half of that amount. So half of 2 pi is 1 pi. So if I go over here to 180 degrees, that's exactly the same as 1 pi radian. So traveling the top half of this circle, traveling a semicircle, gets us to 1 pi radians. And we want to break that down even further here. So we can see that the top half of this circle is broken into 4 equal parts. So this first angle measure here, which is 45 degrees in degrees, we would think about as 1/4 of pi in radians. So we can see this 1/4, but pi has to be included because the top isn't just simply 1, it's 1 pi radians as an angle measure. So I'm traveling 1/4 of the way, so I have 1/4 of pi, and then I'm traveling 2/4 of pi, which reduces to pi over 2, and then I go a little bit further and I travel 3/4 of pi, and then finally I end up at 4/4 of pi, which is just 1 pi. And I can continue on adding that 1/4 of pi every time, so I end up with 5 pi over 4, 6 pi over 4, which in lowest terms is 3 pi over 2, 7 pi over 4, and then concluding, going all the way around, was going 8/4 pi, and 8 over 4 reduces to 2 pi, which we knew one complete revolution is 2 pi radians. Now let's go and take a look at the circle again, but focusing on angles that increase by 60 degrees every time and understanding those same angles in radian measure. So again, the whole entire circle is 2 pi radians going all the way around. So that means that the semicircle, the top half of the circle, is half of 2 pi, so we end up with that 1 pi radians. But here, if we're focusing on breaking this up at 60 degrees and 120 degrees and then getting to 180 degrees, that's taking even thirds. So I'm traveling 1/3 of the entire 1 pi that makes up the top of the semicircle. So I'm taking 1/3 of that whole pi, or 1/3 pi, and then I'm going another third of the way to end up at 2/3 pi, and then finally 3/3 pi to end up at 1 pi. And then I can continue on. So I have 4/3 pi, 5/3 pi, and 6/3 pi as I move around the circle. So this is just looking at a different set of angles this time and how we'd have to do different subdivisions, how I'd have to create this idea of these different fractions. So now I'm thinking about 1/3 of the semicircle on the top. And this last one, I mean, looks a little hectic, but it's because we're now thinking about the 30-degree angles going all the way around, going up by 30 degrees every time. So if I want to take this whole region here from 0 to 180 degrees and go up by 30 every time, I'm breaking this up into sixths. So if I shaded one of these regions here, that's 1/6 of just the top. So remember, I'm just considering the top because the top is the whole 1 pi. That's just the top of the circle. So this portion here would be 1/6. So that means this angle here in radians is a 6 pi, and then 2/6 pi, or pi over 3. We have 3 pi over 6, or pi over 2. 4 pi over 6, or 2 pi over 3 reduced. 5 pi over 6, 6 pi over 6. And then I can see as I continue around, 7 pi over 6, 8 pi over 6, 9 pi over 6, a lot more subdivisions, 10 pi over 6, 11 pi over 6, and finally 12 pi over 6, which is 2 pi. So now let's take a look side by side. So here we have the familiar degrees. Remember, 1 complete revolution measures 360 degrees. And then side by side, with all the same angles measured in radians. So remember, 1 complete revolution measures 2 pi radians. So traveling all the way around, I start at 0 degrees, and then I've traveled 1/6 of pi, then 1/4 of pi, 1/3 of pi, and 1/2 of pi, because remember, pi's right here. So up here is half of the way. I've traveled half the way. And then 2/3, 3/4, 5/6, and then a whole pi. Moving along to 7 pi over 6, 5 pi over 4, 4 pi over 3, then 3 pi over 2, or 1.5 pi. So remember, this is 1 pi, so this is 1.5 pi, 1.5 pi. And then 5 pi over 3, 7 pi over 4, 11 pi over 6, and getting back to 2 pi. So in these examples, we're going to determine the quadrant the angle will lie in, if any, and sketch it. So we have theta equals 5 pi over 4. We want to know, where is 5 pi over 4, in which quadrant? So I'm going to go ahead and start a sketch here. So I'm going to go ahead and remember the quadrantal angles. So I have 0, I have a half a pi, I have 1 pi, and I have 3 pi over 2. So it's kind of like remembering 0, 90, 180, 270, 360 in degrees. So 5 pi over 4, well, what I'm going to remember here is that 1 pi, that's the same as 4 over 4 pi. So I need to go an extra fourth. So 5 pi over 4 is going to be right here. So I need to connect that. So I have, this is 5 pi over 4. So it's going 1 pi and then another fourth of the way. That is my angle theta. So the answer here, the quadrant, is quadrant 3. And now for beta. So beta is negative 5 pi over 6. So remember, negative means that I travel in a counterclockwise direction. So we'll go ahead and again start to label our quadrantal angles. So I'm going to start at 0. I'm going to travel in a counterclockwise direction. I'm going to label this as negative pi over 2, or negative a half a pi, and then negative pi, negative 3 pi over 2. So here I want to think about everything broken up in sixths. So this is negative 1 pi, or it's negative 6 over 6 pi. And if I want to rewrite this so it has a denominator of 6, I can do that as well if it helps me. So this is negative 3 pi over 6. So negative 5 pi over 6 is between negative 3 pi over 6 and negative 6 pi over 6. So I'm going to break up quadrant 3 into 3 equal parts, because here I have negative 4 pi over 6, and then here I have negative 5 pi over 6. So I'm traveling in that counterclockwise direction to find theta, and I'm again, for angle beta, in quadrant 3. So now we look at angle alpha, 8 pi over 3, And hopefully we can recognize this is more than 1 complete revolution. 8/3 is greater than 2. So in fact, I'm going to think about this as an improper fraction. So this is the same as 2 2/3 pi. So I'm going to go around 1 complete revolution, that's 2 pi, and then I'm going to go a little further, I'm going to go 2/3 of the way. So if I go ahead and sketch this angle, so I'm going to go ahead and once again label my quadrantal angles, and I know that I go all the way around, that's 2 pi, so there I am so far, and then I have to go 2/3 of the way. So remember, this is 1 pi, so I want to break this down, this top part down, into equal thirds. So this is going an extra 1/3 of the way, and then this is going 2/3 of the way. So 8 pi/3 is going 2 pi and then 2/3 of the way. So over here is my 8 pi/3 angle. Right, this is alpha, and that happens to be in quadrant 2. And then here we have gamma is equal to 9 pi/2, which again is going around more than 1 complete revolution. So how many is it exactly? Well, 2 goes into 9 4 times with 1 left over, so it's 4.5 pi. So that means I'm going to do 2 complete revolutions. 4 pi is 2 complete revolutions, and then I'm going to go an extra half a pi. So here, if I go ahead and construct my angle, so I have 0, a half a pi, pi, 3 pi/2, and then let's recognize this is the same as 2 pi, it's also the same as 4 pi. So to sketch my angle, I'm going around 2 pi, then another 2 pi, so that was 4 pi, and then I'm going a half a pi. So I'm actually up here along the positive y-axis, so this is my angle gamma, and it's not in a quadrant. It is a quadrantal angle. This is a quadrantal angle. It is not in a quadrant. So now let's see how to convert between degrees and radians. So we'll start by converting degrees to radians, and to do that we multiply by pi/180 degrees, and then we simplify. And the reason we can do this, we can multiply by this, is because this is basically 1. Remember, pi is equal to 180 degrees. But we'll see what happens. So convert from degrees to radians. Which quadrant will the angle lie in, if any? So we'll go ahead and start with 105 degrees, and we multiply by pi/180 degrees. And the reason for that is because now the units of degrees will cancel. So I have 105 pi/180, and we'll reduce to lowest terms and get 7 pi/12. So this is the same angle in radians as 105 degrees. And 105 degrees is in quadrant 2. So I will absolutely admit that finding the quadrant an angle lies in is a lot easier to identify in degrees and radians. But here, 7 pi/12, we should get some number sense. Well, 7/12 is a little bit bigger than 6/12, which is a half a pi. So if I'm a little bit bigger than a half a pi, then that would bring me into quadrant 2. And then here I have the angle 249.8 degrees. So we want to turn that into radians. So 249.8 degrees times pi/180 degrees. Again, my units of degrees will cancel. So that means I will have radians. So I have 249.8 pi/180. Which is kind of an ugly looking answer, so I'm actually going to approximate this answer. So keep in mind that pi is the irrational number that continues on forever, 3.14159, etc. So I'm going to substitute this into my calculator and get the approximation 4.36. So 4.36 radians. So sometimes students get really caught up on, oh, it doesn't have a pi in it, so it's not in radians. But remember that a radian is the ratio of the arc length to the radius. And so that ratio is just a real number. So it can have a pi in it and be exact, or we can approximate the value in this case and get 4.36 is perfectly fine. It is still in radians. We just want to make sure we don't put a degree symbol on it. That would mean a completely different angle measure. And then what angle will this quadrant lie in? 249.8 degrees is between 180 and 270 degrees. So this is in quadrant 3. Now we'll convert from radians to degrees. So we multiply by 180 degrees over pi, the reciprocal, and then simplify. So here we'll go ahead and start by looking at 2 pi over 3. So we have 2 pi over 3 and then times 180 degrees over pi. So we can see that we're going to be left with degrees in our answer. So we're going to have 2 times 180 divided by 3, so that's 360 divided by 3, or 120 degrees. And 120 degrees is between 90 and 180, so we are in quadrant 2. So now, if our answer has a pi in it, the other way we can convert to degrees is to simply replace pi with 180 degrees. So another option was to take 2 times 180 degrees over 3, and we would still get 120 degrees out as our answer. But we could see here in part B that we have 4.25, and this is in radians, right? It doesn't have a degree symbol, so it is in radians. So to convert this, we do have to multiply by our 180 degrees over pi to introduce the degree symbol, to introduce the units of degrees in. So here, I'm going to multiply this all out and approximate the answer. So I'm going to multiply 4.25 times 180 divided by pi, and that's approximately 243.5 degrees. And that's between 180 and 270 degrees, so we are in quadrant 3. Alright, now let's take a look at reference angles using radians. So the following angles have a reference angle of pi over 6. So let's take a look at them. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 all have a reference angle of pi over 6. Because remember what a reference angle is. It's the acute angle that goes from the terminal side of an angle to the x-axis. So 5 pi over 6 here, to get to the x-axis, that acute angle that's made, I have to go another 1/6 of the way of a pi, so pi over 6. And 7 pi over 6, the terminal side to the x-axis, again, makes an angle of pi over 6. And for a reference angle of pi over 4, those would be the angles pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Because again, let's focus this time on 7 pi over 4. The terminal side to the x-axis, the acute angle there is pi over 4. I'm 1/4 of a pi away from the x-axis. So I can see all of these angles having in common that pi over 4 involved in them. And finally, the angles with the reference angle of pi over 3 are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So picking on, let's say, 4 pi over 3, the terminal side, the acute angle that gets me to the x-axis, is pi over 3. That's how far I am away. I'm 1/3 of pi away from the x-axis. So hopefully I can start to see that pattern emerge here with these non-quadrantal angles, and seeing that I can simply think about removing the coefficient and just taking pi over 6, or in this case pi over 4 or pi over 3 as the reference angle. In this example, we want to find each function value. And notice that all of the angles are in radian measure, and we don't want to convert all of these to degree measure. So what we're going to go ahead and do is just start, let's go ahead and look at the first one, sine of pi over 3. So this is an easy one to convert to degrees. So pi is 180 degrees divided by 3, that's 60. So sine of 60 degrees is the square root of 3 over 2. The ideal situation is that you would have all of the angles in quadrant 1, whether given in degrees or radians, memorized for sine, cosine, and tangent. So sine of pi over 3, radical 3 over 2 would be a function value that we would know automatically. But sine of 2 pi over 3 is something that we're going to have to think about. And we have these steps over here for evaluating trig functions at an angle theta in radian measure. So the first step is to simplify the angle theta to lowest terms. So 2 pi over 3 is in lowest terms, so we'll skip to step 2. Based on the quadrant of theta, determine the sine of the trig function. So we'll go ahead and sketch where this angle is at, but the ideal situation would be that you know where the angle 2 pi over 3 is at without having to sketch it. But for now, we will sketch 0, we have a half a pi, we have 1 pi, we have 3 pi over 2. And so 2 pi over 3 is going 2/3 of the way. So here we have, this is going to be pi over 3, and then here we're going to have 2 pi over 3. So since 2 pi over 3 is in quadrant 2, and we know all students take calculus, that the sine function is positive there, we have determined the sine of this overall value. So this is going to be a positive value. And we find the trigonometric function value for the reference angle theta prime instead. So now sine of 2 pi over 3, we know the answer is going to be positive, and it's actually going to be positive sine of the reference angle being pi over 3. So the reference angle for 2 pi over 3 is going to be pi over 3. That is, from the terminal side to the x-axis, the acute angle, right, as we discussed, pi over 3. Well, sine of pi over 3 would be known. We can see it. It's just radical 3 over 2. So we get positive radical 3 over 2. Let's try the next one. Sine of 3 pi over 3. Well, step 1 was simplify the angle to lowest terms. So the 3's are going to reduce down to 1, so we end up with sine of just pi. If the angle is quadrantal, we'll just jump to evaluation. So pi is over here where the coordinate is -1, 0. Sine is the y value, so we end up with sine of pi is equal to 0. Moving on to sine of 4 pi over 3. Well, that's in lowest terms. And we need to figure out where 4 pi over 3 is to determine if the answer will be positive or negative. So 1 pi is 3 pi over 3. So down here we're going to have 4 pi over 3. And then I'll even go one further and just go ahead and label it because we know we'll need it in the next one. 5 pi over 3 is down here. So 4 pi over 3 is in quadrant 3. And only tangent is positive there. So this will end up being a negative sine of the reference angle, negative sine of pi over 3. So negative radical 3 over 2. And sine of 5 pi over 3, so 5 pi over 3 is in quadrant 4, and only cosine's positive there, so we get negative sine of the reference angle, and that's again negative radical 3 over 2. So if we box in our answers, and let's take a close look at least some of them, the quadrantal angle, pi, gave us a value of 0. But all of the other angles, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, they were all radical 3 over 2. The only difference was the sign, whether the answer was positive or negative. So if we can determine where this angle is on the unit circle and whether the trig function will be positive or negative there, then we only need to evaluate the trig function at the reference angle and just slap on the sign, right, whether the answer is positive or negative.